All right, in this video, we're going to talk about Newton's second law and just building on what we've learned from before. Okay, so for Newton's second law of motion, objects are accelerating. And so acceleration is the rate an object's velocity is changing. So it can be a change in speed and or a change in direction. So anytime something is turning, it also is accelerating. Acceleration is a vector quantity. I guess I should point out, here's the formula for acceleration. Acceleration is change in v over time. So I can write that as acceleration. Scientists like to use deltas, so triangles for change in. Okay, so this triangle means change in. We could also write the acceleration equals v final minus v initial over t. Okay, so those are the equations for acceleration. For the acceleration, well, I want to just kind of point you at like this picture here. Acceleration can be thought of as like how fast your speedometer is moving. Okay, so how your speedometer is changing is your acceleration. So if your speedometer changes from 10 miles per hour to 20 miles per hour over 1 second, you've changed by 10 miles per hour per second. Okay, so acceleration does have weird units because if we look at velocity is in meters per second, and we're dividing by time, which is also in seconds. So acceleration can be thought of as having units of meters per second, so telling you how many meters per second your speed changes by per every second. A lot of times we'll write this as meters per second squared. Okay, a second squared doesn't really mean anything. It just is, it's more convenient to write than meters per second, although they mean the same thing. Okay, so again, just to illustrate that your acceleration can change, or you can accelerate in lots of different ways. So if we look at this original car here, we can accelerate by going to some later time where you're going faster. You can accelerate by having your direction change, so that from one car to the other, only the directions change, not the actual speed. And then you can also change by changing both speed and direction. So you can see that now we're pointing downwards and also going faster. And then, of course, the last way to accelerate is to stop. Okay, so when it hits the ground, it's going to stop very quickly, and that's a really big acceleration. Okay, just to review, we've got for no acceleration, which is with Newton's first law we've already talked about, we got distance equals speed times time, and we can also look at velocity as a change in position divided by time. Now that we're accelerating, we can enter in a couple new formulas. One, distance equals 1/2. The two velocities, VI means your starting velocity, VF means your final velocity, times time. And then acceleration equals the difference between velocities divided by time again. So those are new velocities. Okay, so this part right here just means your average speed. And if your speed's not changing, if VI and VF are the same, this reduces to the formula we already had. Okay. So, doing an example problem, we want to look at how do we do these problems with the formulas we have. So a car accelerates from 0 to 20 meters per second over 3 seconds. What distance has it moved during this time? So we're going to start off with drawing a picture. So here's my car. And originally v equals 0. And then at some later distance, which I don't know, now the car is moving at 20 meters per second. Do my knowns and unknowns. So my knowns first and then my unknowns. So I know that VI, my initial velocity, is 0 meters per second. I know my final velocity is 20 meters per second. I know my time is 3 seconds. Whoops. My time is 3 seconds. My unknowns, I don't know what distance I've moved, and I don't know what my acceleration is. Okay, now the problem doesn't ask for the acceleration, but I might need to know that, because when I go to my equations, so what equations do I know? So the new equations I have for accelerated motion is distance equals 1/2 VI plus VF times t. Well, if I look at that equation, I don't know distance, okay? I do know VI, and I do know VF, and I do know T. So it turns out for doing this one, I don't need to know what my acceleration was, okay? So I can just use this one equation. I don't have to do anything else, so it didn't matter that I didn't have acceleration in this case, okay? So now I can solve symbolically first, which since I was asked for distance and I have distance, I've already got that done, so I can plug in numbers. Distance equals 1/2. VI is 0. VF is 20 meters per second. And T is 3 seconds. So now I can take 0 plus 20 is 20. Divided by 2 is 10. And 10 times 3 would be 30. Units, seconds cancels. This is meters, which is a distance. So check your answer. Distance is 30 meters. Okay. Does that seem reasonable? Yeah, I think a car could go 30 meters in 3 seconds pretty easily. Okay. And that is a distance, so that seems reasonable. Okay. Come on. All right. For Newton's second law, okay, it has an equation form where it's a lot of times it said F equals ma, but that's not true. It's really F net equals ma. F net is equal to this symbol means sum of. So F net is the sum of all your forces. So Fn just means like different forces. So like force 1, force 2, I just sum all the different forces up, and that equals my mass times acceleration. When we look at units, mass has units of kilograms. Acceleration has units of meters per second per second. So force is those two units multiplied together. So force has units of kilogram, meter per second per second. Since that gets kind of cumbersome and hard to write that all out, force then we say has units of newtons. Okay, so we name it after Newton. Okay, to give you an idea of how big a newton is about 1/4 pound. Roughly. It's not exactly 1/4 pound, but roughly 1/4 pound. Okay? So if I wanted to find, let's say if this was a 10 kilogram object, and this force was 20 newtons, and this force was also 20 newtons, and we'll say this force is 10 newtons, and I want to know how much is this object accelerating, I would add up all these forces. So 20 newtons to the left plus 20 newtons to the right would be 0 newtons. And so my F net equals 10 newtons up, and that equals my mass, 10 kilograms, times my acceleration. So in this case, my acceleration would equal 1 meter per second per second. Okay? So, sample problem. A child is being pulled on a sled. The combined mass of the child and the sled are 50 kilograms. The force of friction on the sled is 10 newtons, and the parent is pulling with a force of 60 newtons. What is the acceleration of the child and the sled? So first I'm going to draw a picture. So I've got the child and the sled. Okay. So maybe I'm terrible. So there they are. They have legs being pulled by a parent. Okay. I certainly didn't have to go that detailed. And if I look at what forces are on the child, there's weight, there's the normal force, there's friction pushing back on the sled, and then there's the applied force of the parent. Okay? A lot of times I want to simplify that, and I just want to look at, okay, there's the child and the sled, there's the normal, there's the weight, there's the applied, and there's friction. Okay? My knowns and unknowns. I know that the applied force is equal to 60 newtons. I know the friction force is equal to 10 newtons. I know the mass of the child and the sled together is 50 kilograms. Okay? I know that, I guess that's all I know. Unknowns, I don't know the acceleration, and I don't know F net. Okay, so I don't know those two things. When I look at equations, I know that F net equals ma, and I know that F net equals the sum of the forces. Okay? So, let's solve this. Okay? So first I'm going to look at F net. F net equals, now, weight and normal, because the child's not accelerating up or down, those balance each other out, so those sum to 0, so I'm not going to include those. So F net then equals my applied force minus friction, because those are in opposite directions. Okay? So now I know that applied force minus friction equals mass times acceleration. And if I solve that for acceleration, acceleration equals applied minus friction divided by mass. And I'll let you plug in the knowns and figure out what the unknown acceleration would be. All right, the last sample problem, we have a 54 kilogram woman is standing in the elevator accelerating upward at 2 meters per second. The scale reads 637 newtons. What does the woman actually weigh? So here we have a woman. Oh, she's standing on a scale. The scale pushes upwards on the woman. Weight pushes downwards on the woman. Okay, so we've got, again, to make that simpler, we've got the normal force from the scale, and then we have weight. Because the woman's accelerating upwards, I didn't do a very good job drawing it, but normal is greater than weight in this case because she's accelerating upwards. Okay? And I think I'm going to let you guys finish this up. Knowns and unknowns should be similar to what we had before. Equations should be similar. Okay? See what you can do and see if we can do this, finish this one up together. All right, so that's it. Oh, one last thing. Graphing accelerated motion. I forgot to make a slide for this. So we should have already seen this in lab, but if I'm graphing accelerated motion, position versus time, you should find that your position, if you're speeding up, okay, that would be speeding up. If you're slowing down, okay, slowing, come on, gee. And then you could be speeding up backwards. So like this is speeding up backwards, or you could be slowing down backwards. Okay? All right, that's it then. See you in class.